All right, you guys. Okay, I'm trying to get my screen set up here. I if I look over here, it's because that's the screen where my face appears, but that's you guys over there. Okay. Occasionally I get messages and so on about this, and I need to have a screen so I catch those. Okay, so a second part of Riemann sums here. It says let's actually do this estimation now that we've gone over the vocabulary. And to keep the calculations under control, let's use a maximum of 4 subintervals. It just gets, you're just calculating and calculating. So the first thing is we want 4 subintervals. And so how many cuts will we need to make in order to make 4 subintervals? Well, I'm gonna cut this thing, and it can be completely arbitrary where you cut them. There's no rhyme or reason really to it, so I'm not going to worry about it. So I'm going to cut here, and then I'm going to cut again here, and then I'm going to cut again here, just for the heck of it. Okay, so if I make 1, 2, 3 cuts, then I will have 1, 2, 3, 4 subintervals. So 3 cuts are necessary. So it says draw vertical lines in the figure representing the partition. So here's where I am partitioning this. Okay, drawing rectangles that appear to represent the area of the curve over the subinterval. And one restriction is that the height must correspond to at least one value of the function over the subinterval. So what that means is when I decide on the height of this particular rectangle here, I can't make it lower than this here, and I can't make it higher than the very highest point on that subinterval. So I'm not allowed to say, for a Riemann sum, I wouldn't be allowed to say that the area of this is approximately 8. That would be an overestimate, but the reason it would be an overestimate, the reason it wouldn't be correct is that it would exceed this value here. So as long as you pick a value between the lowest and the highest points on the subinterval, it's a perfectly acceptable Riemann sum. And so what I'm going to do is I'm going to try to chop this so that the area above and the area below seem to basically cancel out. So if I say that that area there is 6, then what I'm saying is, well, this little extra and that little underestimate and that little overestimate, or vice versa, those will cancel each other out. Okay, and it really doesn't matter. Okay, it does not matter. As long as you pick any height between the min and the max, you're fine. Okay, so then this next section here, well, the subinterval goes to there. I don't know. I'm going to aim for something. You know what? I'll just make my life easy and go right here. Okay, I'm just going to chop there. Again, as long as I'm between the highest point on the interval and the lowest point on the interval, it's perfectly fine. And you can see I'm kind of being lazy about this, and I'm picking integer values so far. Okay, in this subinterval here, I have to pick a height between this point here and that point there. So I'm going to pick right here as my height, and that's probably not the best actually, because this is a way bigger area than that is right there. And so actually I'm going to change that one. Let's see if this alerts. And it doesn't matter. The point of this is not really for super accuracy. We'll learn way more accurate methods later on. I'm actually going to cut that one, I think, here. I think that's what I'll do. And what I'm saying then is this area is approximately equal to that area. And some of you looking at this will say, no, I'm way off. I should have a much better place to do this. Okay, and then finally, this last one, I need to pick something between here and here. And oh gosh, you know what? This one, I think I will just go halfway. Okay, I think this one I'll just actually go like this. Okay, all right. And so what I'm saying is these 4 areas, 1, 2, 3, 4, will basically represent the overall area under this curve here. Okay, so there is not one correct answer to this. If I did this on a different day, I might have completely different values for everything. So remember, this is x sub 1, this is x sub 2, this is x sub 3, and this is x sub 4. And you'll notice that 4 corresponds to this, which is exactly what we want. And this, instead of calling this a, we will call this x sub 0. Okay, and so the first subinterval goes between x sub 0 and x sub 1. So that goes between 0 and 2. So the width of it is 2 units. As we can see, it's 2 units wide. Okay, the x coordinate of the point at which we evaluate the function. So that is our decision, okay? Where do we want to evaluate this? But it looks like I've chosen here as my point. And so that is just a tad underneath. It looks like 1. I mean, maybe you could argue it is 1. Let's just say for the sake of discussion that that point right there is at x equals 1. Okay, and that's a judgment call. Maybe I'm off by a little bit, but this is just an approximate anyway. Okay, the height of the y coordinate chosen. So if I pick that point right there, that's C. I get to choose that. The height of the function here is 1, 2, 3. And so that is the function evaluated at 1, and I'm estimating that to be at about 3. And so then my area is basically this height multiplied by that width. So you'll notice it's f of c sub 1 times delta x sub 1, which is equal to 3 times, not this number, not 1, but 2. And that area is equal to 6. And that makes sense because when I drew this line in, what I was saying was this area here was basically an area of 6. Okay, now moving on to the second subinterval, that goes from x sub 1 to x sub 2. It goes from 2 to 6. So the interval goes from 2 to 6. The width of the interval is 4. So delta x sub 2 is 4. And where do I want to evaluate this? Well, I have some choices. I could evaluate it here and say that that's my height, or I could evaluate it here. And I could say I want to evaluate it anywhere as long as the height corresponds to this. So I'm going to say that I'm going to evaluate that rectangle's height at what, about 3.2, we'll call it. Okay, and it doesn't matter. As long as you pick a point in between here and here, between x sub 1 and x sub 2, you're fine. It does not really matter. Okay, so I'm choosing 3.2. So 1, 2, 3.2, just a little over 3. Okay, and the height at that point, f of c sub 2, meaning the height evaluated at 3.2 is indeed a height of 2. So like so, this height is 2. Okay, and so the area of the second rectangle, this rectangle in here, so this rectangle's area in there is equal to the function evaluated at my choice 2 multiplied by the width of that subinterval. And so that value of the height is 2 times the width of the interval, 4, and that equals 8 square units. And that makes sense with what I have here. This rectangle here is a 4 by 2. 1, 2, 3, 4 by 2, and there it is. Okay, and then likewise, I just go down the line doing this. So my third interval goes from 6 to 8. So it goes from 6 to 8, and the width of it is 2 units. Delta x sub 3 is 2 units wide. And I'm going to evaluate it right here in the middle. So it looks like I'm evaluating that at 5. So the third choice that I make for a height, I'm going to say that that is equal to 5. And then the y coordinate there is 1, 2, 3, 4, 5, 6. So f of c sub 3, which is f of 5. So the function evaluated at 5 is 1, 2, 3, 4, 5, 6. Okay, and then finally the area of this is equal to the function evaluated at the third choice times the width of the third subinterval. So we just worked out f of c sub 3, and that was 6. And the width of this interval was 2. And so that gives me an area of 12. And that makes sense because this area here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I don't want the notation to get in the way of your understanding. We're just calculating how many units of area there are underneath there. Okay, and then finally the fourth subinterval goes from 8 to 10. So the width of that last subinterval is 2. And I'm going to evaluate that one. I said I was going to approximate it right here, right there. And so that is going to correspond to something like 9.2, I would guess. So I'll say I'm going to evaluate it at about 9.2. And the function evaluated at 9.2. Okay, I'm getting a message. I need to stay in the call here. It thinks I'm just presenting to myself. Okay, so the value of the function evaluated at 9.2 is 1, 2, 3, 4, 5, 6.5. So that would be 6.5. Okay, and then finally, the fourth area is the function evaluated at my fourth choice on the x-axis times the width of the fourth interval. And so that height was 6.5. And I'm going to multiply that by the width, which was 2. And that gives me 13. And so what I'm saying is this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 13. The area of this is 13. Okay, so the norm, the widest partition here looks like it was 4. So this was the widest one. So I put a 4 there for that. And then when it talks about the area, I'm just adding these all up. And so this is what, 20. So 33 plus 6, about 39 total square units. Okay, this question didn't give us any units to work with for area, and so I'm just going to leave it as 39. You could write 39 square units, and that's fine, but not necessary. Okay, all right, so this, as you can see here, we are adding up this quantity 1, 2, 3, 4 times. The only thing that's changing here when I write each of these down is the subscripts change from 1 to 2 to 3 to 4. So it's always exactly the same thing. So this is the formula for the Riemann sum. And what it says is this sum of, this means the sum of n subintervals. The sum of all those areas is the summation of the function evaluated at each point from 1 to n. So k would start as being a 1, and then it would go to a 2, and then a 3, and then a 4. And then you multiply it by the width of each subinterval. So it says write it for this situation. So I'm going from 1 to 4. So I do sort of housekeeping numbers, 1, 2, 3, 4 up top. And then what it's saying is the sum, the sum of this thing with 4 subintervals is equal to, so the first one is the function evaluated at c sub 1 times delta x sub 1 plus the function evaluated at c sub 2. And I think of that as choice 2. I got to choose where to do that, times delta x sub 2 plus, and then the same thing again, the function evaluated at c sub 3 times delta x sub 3, and then the function evaluated at c sub 4 times delta x sub 4. So this is a concise way of writing this whole mess out, okay? And then it says use it to evaluate the Riemann sum. Well, we literally did that up here. So if you just go through it literally, what it's saying is f of c sub 1, well, that was 1. So f of 1 multiplied by delta x sub 1, which was here 2, plus, and then f of c sub 2, well, we said c sub 2 was at about 3.2, times delta x sub 2, which right there is 4. Okay, and then we evaluate this at c sub 3, which was 5, times the width of the, the width of the third interval. What is the width of the third interval? Right there, 2. Plus, and then our last rectangle, we evaluate that at c sub 4, which we said was 9.2, and we multiply that by the width of the fourth subinterval, which was 2. Okay, so you can see it's exactly the same series of calculations that are shown up in the table here, but we're just doing it using the formula as specified. Okay, so f of 1, I'm going to peel that right off the function. So f of 1 is right there. That was 3. So this is 3 times 2. Okay, the function evaluated at 3.2, here, if we go to 3.2, 1, 2, 3.2, that height is 2 there. So that would be a 2 times 4. Okay, the function evaluated at 5. So we would evaluate the function at 5. When x is 5, 1, 2, 3, 4, 5, 6. So that height is 6. And that we had that in the table here. F of 5 is 6 times that width 2. And then finally, f of 9.2, which we said was 6.5, and we multiply that by 2. So we end up with 6 plus 8 plus 12 plus 13, which is exactly the same thing that we had before. And 8 and 12 makes 20. 33 plus 6 more is 39. So this is just to show you that this nice little formula here works really well for the Riemann sum. And that is the end of that video, okay? So I'm going to stop presenting and then turn off the camera. Okay. All right. See you at the next video. Bye-bye.